Hello, everybody, and welcome to the video for week 7. A few quick reminders. Your homework is due Monday at 11:59 p.m. You have a quiz on this video due on Tuesday at 8:30 a.m. So what were the key takeaways from this week? Well, the big thing we did on Tuesday was discuss how do you solve polynomial congruences. So like f of x is congruent to 0 mod n, where f of x is some polynomial of integer coefficients. And so the way we did this is first we used the Chinese remainder theorem and the factorization of n to really split this into solving multiple congruences, but now where n is just a power of a prime number. Then we talked about how you solve congruence modulo a prime power. And the first thing you solve it mod p, that you can do by guess and check basically. Something that's helpful there is Lagrange's theorem, which tells you that when you're working mod p, when p is a prime number, then the number of roots is at most the degree of your polynomial f. And then to go up from roots mod p to roots mod some higher power of a prime, well, the main tool we had that doesn't always work but often works is Hensel's lemma. Good, and so we talked about how to use that on Tuesday. We did some examples. This whole process was summarized in the lecture on Thursday, and in particular, if you look at the slides from Thursday, you'll see a summary going into a little bit more detail than I did here. Good, and then after that, the main thing we did on Thursday was discuss, well, the group of units modulo n, un, and then Euler's phi function, which was the size of this group. The big result was Euler's theorem. So this told you if I took something co-prime to n, so something in un, and I raise it to the phi of n power, then I get 1 modulo n. When in the case of n prime, this was just Fermat's little theorem, which we talked about first, actually. And while the big thing is this makes computing powers a lot easier. This lets us reduce the exponent when we compute powers modulo n. Then we also saw right at the end of the class that this gave you a useful way to compute inverses. And then as an application of that, we saw a way you could simplify the formula for a solution to a simultaneous congruence that shows up in the Chinese remainder theorem. Okay, so I want to talk about, well, next week we're going to do, we're really going to use these powers a lot, and I build on some of these things like Lagrange's theorem, and we're going to discuss on Tuesday roots of unity. So these are solutions to x to n is equal to 1. And in various contexts, we'll discuss those. And then once we have that on Tuesday, then on Thursday, we're going to talk about how those get used in cryptography. So that's where we're going with all this. So this application to computing powers in particular is very important. And Lagrange's theorem is also actually quite important. Today, I just want to go into a little bit more detail about where some of these things here were coming from and how they fit in to a broader schema of things. So in particular, I want to tell you where Hensel's lemma comes from. This tool we use to lift from mod p to mod p squared and p cubed and so on. And I also want to just talk briefly about a broader context for Euler's theorem. And so Fermat's little theorem is a special case of Euler's theorem. Euler's theorem is actually a special case of some more general result. I just want to explain where you'd find more about that if you're curious. Okay, so first Hensel's lemma. Fun thing about Hensel's lemma is it's actually the exact same as Newton's method. So Newton's method is something that many of you will have seen in a calculus class, though maybe not all of you. But this is a simple method you can use to try and find or approximate a root of a polynomial with real coefficients. So if you have f of x is a polynomial with real coefficients, Newton's method is a way to try to find a root. Okay, and so here's how it works. You have your polynomial f of x, and so you look at y equals f of x. And actually, for Newton's method, it's not so important that it's a polynomial, but let's just pretend it's a polynomial anyway. And well, the first thing you do is you just make a guess. You say, okay, maybe you do some numerical approximation. You try to find something that looks like maybe it's near a 0. So in this case, I find this x naught that is close to a 0 of x, a 0 of f. And I want to try and get from this x naught to something that's even closer. I want to try and sort of make a new approximation that's better starting from this one. Well, what do I do? Well, if I look at sort of f of x naught, so here, this is f of x naught, well, then I can just draw sort of now the tangent line. Well, I don't know if I can draw a tangent line. I can try and draw a tangent line through that point. And now if I look at sort of, like I know sort of the tangent line is supposed to be a good approximation of the graph of that function at that point. So now I can sort of look at where that, like instead of looking where the graph intersects 0, like that's what I'm actually trying to find, I can look where this tangent line sort of at y equals f of x naught looks like, intersects 0. And I get sort of this point here. So this is my x1. And sort of if I am in good shape, like if I sort of got my initial 0 close enough, my initial guess close enough, and if sort of my function is not too bad, then sort of this new approximation x1 will actually end up closer to the actual root I'm looking for, like happened in sort of this example. Like now this x1 is sort of closer to this point right here that I'm actually looking for. And then sort of now I can sort of repeat the process with x1. I could sort of look at f of x1, draw the tangent line, and I'd sort of get sort of, like my picture is not big enough to accommodate this, but and somehow I'd get sort of even closer to a root, and I sort of repeat and repeat. And in sort of a good situation, this will actually sort of converge to a root. The sequence of sort of approximations will really converge to a root of f. Okay, so that's the idea of Newton's method. I mean, why does this work? Well, and so the point is that like it's hard to sort of find the zero of a polynomial. Like there's no good formula for it. But like if I'm just sort of looking for where the tangent line sort of intersects the x-axis, that's simple. Like that's sort of, I have a formula for the tangent line. This is y is equal to f of x naught plus f prime of x naught times x minus x naught. Well, it's really easy to see like when this is 0. And so this is 0 exactly at the value x1, where sort of, I'm going to write that in a funny way. I'm going to write x1 as sort of x naught plus sort of some small epsilon. So I'm moving a little bit away from x naught. And so then, and the reason I write this is because if you sort of expand this out and say, when is this 0? It's exactly when epsilon solves f of x naught plus epsilon times f prime of x naught is equal to 0. Okay. And so, well, then the point is, this looks a lot like the equation that shows up in Hensel's lemma. Let me make that completely precise. So if we look at Hensel's lemma, this says that if f of x, so I have some approximation, so I have a root xe minus 1 that's congruent to 0 mod p to the e minus 1. And I want to sort of go up from that to a sort of some xe that's now a root modulo p to the e. Well, and so then how do I find it? I say, as long as, so when this applies, so when the GCD of, when sort of f prime is sort of non-zero mod p, then, let's write that. E minus 1, it's not 0 mod p. This is sort of when Hensel's lemma applies. Well, so I want, and if I want a root sort of mod p to the e that lifts my root mod p to the e minus 1, I should get that by sort of adding some multiple of p to the e minus 1. So sort of some multiple of k times p to the e minus 1. And then when we wrote down Hensel's lemma was sort of how to find k. So we said k solves the equation where I take sort of f of x e to the minus 1. This is sort of, because this is congruent to 0 mod p to the e minus 1, I can sort of divide this by p to the e minus 1, and I get an integer here. And I sort of look, so that this is just some integer, and then I'm sort of trying to solve sort of this integer plus k times the derivative of x e to the minus 1 is congruent to 0 mod p. Well, this equation here, if I sort of multiply everything by p to the e minus 1, is really the same as saying f of x e minus 1 plus k times p to the e minus 1, f prime of x e to the minus 1, is congruent to 0 mod p to the e. So, and if you look at that, like this number k times p to the e minus 1, this is sort of playing the same role as epsilon in Newton's method. You sort of go back, I sort of have, I'm adding epsilon to sort of my initial approximation. Here I'm sort of adding sort of k times p to the e minus 1 to sort of my initial root, and my sort of new one. And sort of how am I solving for it? Well, I'm solving for this thing being 0. If I sort of called this epsilon, this looks exactly like this formula here. Good. So somehow like I'm actually really doing Newton's method. I mean, some of the idea is I think of this x e to the minus one since sort of is congruent to 0 mod p to the minus one. Like it's very close to being a root mod p to the e. Like sort of it's not divisible by p to the e necessarily, but it's divisible by p to the e minus one. So like sort of something that's sort of close to being a root, like this x naught here. And then when I add sort of a multiple of p to the e minus one, I mean, that's something I'm thinking like I'm adding something that's sort of close to 0, like when I sort of think mod p to the e, when I think mod p to the e. I mean, somehow like if I'm thinking mod p to the e, like being close to 0 sort of somehow means you're divisible by like a large power of p. So you should actually think of this sort of because we're working mod p to the e as like adding some small thing, just like sort of we're adding sort of some small thing here. And I'm sort of looking for which small thing I add, and then I sort of end up solving this like exact same tangent line equation. So actually, I mean, sort of, I like this a lot because this is very close to the area of number theory I do research in. I mean, somehow you can sort of go further with this idea and you can actually sort of introduce a notion of distance called p-adic distance, where sort of large powers of p are small. And then you can sort of do you can do sort of geometry sort of with p-adic distance instead of regular distance. And this is sort of actually what I do research on. Okay, I won't say anything else about that, but if you're curious about that, you can always send me an email and I can give you a good reference to look at. But somehow, anyway, the point is this, like Hansel's lemma really is just this Newton's method that you hopefully know from calculus. In particular, like when you prove Hansel's lemma, I mean, you basically use the same idea. So to prove Hansel's lemma, I sort of should just write like f of x. Well, this is a polynomial on x, but I can also sort of recenter it at sort of using the variable x minus xe minus 1. Or in other words, I can sort of like write down like the Taylor expansion around this sort of point xe minus 1. And so I get sort of f of x is sort of f of, so this number f of xe minus 1 plus f prime of xe minus 1 times x minus xe minus 1 plus sort of something here. And so whatever this stuff is, it's divisible by sort of x minus xe minus 1 squared. So then sort of when I plug in sort of this number I'm trying to sort of make be a root, I get f of x plus k times p to the e minus 1 is equal to f of x e minus 1 plus f prime of x minus 1, and then sort of, so this is supposed to be, sorry, I wrote the wrong thing here. This is supposed to be x e minus 1 here. And so I'm adding some epsilon to it, where my epsilon is k times p to the e minus 1. So I get f prime of x e minus 1 times k p to the minus 1. So this is sort of this minus x e minus 1. And then sort of this term I get over here like is divisible by p to the 2e minus 2, which, okay, like since I'm working mod p to the e, I'm going to work mod p to the e, and sort of e is at least 2. Like this is 0 mod p to the e. So when I work mod p to the e, this goes away, and I really just get sort of this value of f of x e minus 1 plus k times p e minus 1. So f of my initial approximation plus some epsilon is given by this formula that showed up on this previous slide. So this f of x e minus 1 plus f prime x e minus 1 times k p to the e minus 1. And so if I'm sort of want this to be 0, well, then I just want this to be 0. And sort of, again, sort of undoing this step right here, just sort of factoring out the p to the e minus 1, this is exactly when f of x e minus 1 over p minus p to the e minus 1 plus this multiple plus f prime x e minus 1 times k. I factor out this p to the e minus 1 using my I could factor out a p to the e minus 1 here. This p to the e becomes just p, that this is 0. This is exactly what sort of Hansel's lemma told us we needed to solve. Okay, so that's how you can justify Hansel's lemma. Good. So the next thing I want to talk about, so sort of new topic, is just some context for Euler's theorem. And so just like sort of earlier in class, like it was sort of useful to introduce the notion of a field to sort of like give some sort of idea of like something that like behaved like the rational numbers or complex numbers or real numbers. I want to sort of start by sort of just introducing the idea of a ring. So a ring is sort of captures some other type of number system. And so let me sort of give, like, this is not really a definition, it's sort of just like a vague idea. So a ring is a number system where you can add, subtract, multiply, but not necessarily divide by sort of non-zero numbers, satisfying the expected rules. So for example, the integers are a ring because I'm sort of no longer, like the integers weren't a field because I couldn't divide by non-zero things, but they are a ring. I mean, so ring, I don't worry about this division stuff. The integers modulo n. So in their book, that's written sub z subscript n. I think I've written that before in class as z mod nz. You might see this in other sources as well. This just means sort of the integers modulo n, like I can sort of add 2, I can multiply 2. Not everything non-zero has an inverse unless n is prime, but sort of this still makes sense. Like if you forget about that division rule, you're okay still. So this is a ring. Any field is in particular a ring. So like the rational numbers, the real numbers, the complex numbers, those are all rings. And sort of we saw sort of other interesting things. We've seen at least one other interesting example on your homework for this week. I think it's for this week, or maybe it was, I think this was actually, sorry. Maybe, yeah, I think it was your homework 5. We saw the ring z brackets square root of -5. So this was sort of all the complex numbers you can write as a plus b times the square root of -5. And so if you add 2 such things, like it stays in that form. If you multiply 2 such things, it stays in that form. So this is sort of actually a ring. And this sort of ring is sort of similar in some ways to integers, but sort of dissimilar in some ways. So for example, this exercise you did basically shows that there's not like factorization, unique factorization into primes in this ring. Okay, so this stuff we'll talk about a little bit more later on in the class. But good, so we have rings, and then whenever we have a ring, we can sort of take the units inside of it. So the units in a ring are just the elements with inverses. In general, like if R is a ring, I sort of just write R cross the units in R. So for example, the units in the integers, well, are just plus or minus 1. Like the only integers that have a sort of a different integer you can multiply them by to get 1 are 1 and -1. If I sort of take the integers modulo n and I look at the units there, well, by definition, that was sort of what we called un in class on Thursday. So this, another way, this is just all of the residue classes co-prime to n, or not sharing a factor with n. If I have a field, then sort of the units are just sort of everything non-zero. So like q cross is q minus everything in q except 0. R cross is everything in R except 0. C cross is everything in C except 0. And sort of by definition, basically a ring is a field exactly when the units are not 0. I should be a little bit careful just because I'm playing fast and loose with definitions. Depending where you look, like a ring, so the multiplication in a ring might not be required to be commutative. But sort of here in this class, all of the rings will encounter the multiplication sort of is commutative. So A times B is the same as B times A. If you sort of allow sort of non-commutative things, like then you can sort of like allow like matrices, for example, where A times B is not B times A. But we won't talk about that in this class. So whenever you do this, as you start with a ring, you take the units. Well, these are something called a group under multiplication. So a group sort of axiomatizes the rules for when you just sort of have like addition or multiplication. So you just have one operation instead of 2 operations, but sort of you have inverses for that operation. So for example, like the integers with addition form a group because you can sort of add 2 integers and you can sort of, you have sort of 0. So every time you add 0 to something, you get back to yourself. It's sort of called an identity element. And then sort of, if you have any number, you can add minus that number to itself to get 0. So you have sort of additive inverses. So that's a group, sort of the integers modulo n, where I sort of use addition. That's also called, this object called a group. If I look at the units modulo n, so this un, with multiplication of my operation, that's also this thing called a group. So more generally, if I take like any ring with multiplication, so I take the units and sort of the operations multiplication, that's this sort of thing called a group. I'm not defining a group because we don't really need this idea, but if you look in section 8.3, you can see a little bit about like what is a group and how is this axiomatized, and sort of how you axiotize like the right rules for an operation that has inverses. And this is sort of an interesting thing to do. And if you find this stuff appealing, sort of like sort of writing down like axiommatizations for like different types of operations, like different types of objects like fields and rings and groups, then you would probably enjoy Math 5310 / 5320. These are sort of abstract algebra courses, and that's where you learn about these ideas of groups, rings, and fields sort of more generally. Whereas sort of really in this class, we just sort of use some specific examples, and I'm just sort of mentioning this broader context. We won't actually sort of use it too much. Good. So now to connect back to what we've been doing, I just want to point out like Euler's theorem is actually a special case of something called Lagrange's theorem for groups. So if you want to see what this says, if you want to see this says and how to prove it, you can look at section 8.3.12 in the textbook. It's actually sort of once you've set up the ideas, it's not too hard to prove it. What this says is if you have any group G with sort of a finite number M of elements in it, then if you take anything in that group and you sort of compose, like you multiply with itself, you apply the operation to itself M times, then you get sort of the identity element. So that identity element is sort of thing that sort of, when you hit it, you combine it with something else using your group operation, you just get back to where you started. So this is sort of a general theorem that applies to any finite group, so in this like abstract world. Let me give you two examples that illustrate this. So the first is like, if I look at the integers modulo n with addition as my sort of group law, so like to combine A and B, I sort of add A and B mod n. Well, we know there are sort of n residue classes modulo n. So this is a group of sort of n elements in it. And it's sort of trivial that sort of if I multiply any element in that group by n, I get 0. So this 0 is identity element, so if I add 0 to anything, I get sort of back to where I start. I get that thing back. So this is sort of an example, actually, sort of a trivial example of Lagrange's theorem. And the group of integers modulo n, if I multiply anything by n, I get 0. And of course, like we've seen that, and that's sort of obvious to us because we know n times x is divisible by n, and so that means it's 0 mod n. But this sort of, if you fit in this broader abstract context, this is an instance of Lagrange's theorem. Another example is Euler's theorem. This is sort of, and sort of somehow viewing Euler's theorem as an instance of Lagrange's theorem is probably the simplest way to prove it, although you can sort of write down the proof without introducing groups. And so if my group is sort of UN, so the units modulo n with multiplication, well, the size of that group by definition is phi of n. And so if I sort of take x to the phi of n, I get 1. And so 1 is the unit, the identity element in this group because my group operation is multiplication and 1 times anything is just that thing again. So x to the phi of n is congruent to 1 mod n. This is Euler's theorem that we talked about, and this is sort of a special case of this Lagrange's theorem for groups. Okay, so again, this was very vague. If you want to learn more about that, take abstract algebra or sort of look over this section 8.3 in the book. It's pretty fun stuff. Going forward, we're just going to use the Euler's theorem. So you don't need to know this general context. I just sort of, for broader perspective and sort of culture, I thought it'd be fun to mention it. Good, so I'll see you guys all in class on Tuesday.